Hey everybody, this video is going to cover a review on radicals. So to start off, we're going to begin looking at simplifying radical expressions. To start, we want to go ahead and go over some vocabulary here. If you look at the top left of your screen where you see that square root of 3, we want to make sure that we understand what that pink symbol means. That pink symbol is called a radical. The green number, which is the number under the radical sign, we call that a radicand. And so we want to make sure that we understand what it means for a square root to be in simplest form. So bring your attention over here to the right side of the screen. A square root is in simplest form whenever the radicand contains no perfect squares, when the radicand is not a fraction, and when there are no radicals in the denominator. So again, when we say radicand, that's just the number under the radical. So rereading criteria 1 and 2, this really just says that the number under the square root cannot be a perfect square, and the number under the square root cannot be a fraction. So let's just dive in and review on how it is that we simplify these radicals, these square roots. So one of the methods that we've looked at this year was creating a factor tree. To create a factor tree, what you do is you break down the number into a product of two numbers. So just break it down. What two numbers multiply to give us 60, for example, here. And then you keep breaking down these branches until you end up with prime numbers. After you get those prime numbers, I like to circle them, and then you replace the number in the square root with those prime numbers. This will make sense as we look at some examples here down below. So to start, we're looking at the square root of 54, right? If you're not sure how to break down some of these numbers, what I always like to do is check to see if it's an even number. If it's an even number, then I know I can divide it by 2. So for example, I know 54 is even. I know 2 times 27 would give me 54. And I know that as I break down these branches, I want to circle my prime numbers. So 2 is prime, so I'm going to circle it. So that means I'm done with that branch. 27 can be broken down into 3 times 9. 3 is prime, so I can circle that one. And then 9 gets broken down into 3 times 3. And so we've broken down all of our branches until we ended with prime numbers. And I know that I'm done because if I were to try to keep going, if I try to break down this 3, I would just get, well, only thing that multiplies to give me 3 is 1 times 3. 1's prime, but then I'd keep going with the 1 times 3. I'd be going on forever, essentially, right? So you stop when you get to prime numbers. Remember that prime numbers are numbers that can only be divided by 1 in itself. So once you break down all your branches to a product of prime numbers, we're going to replace that 54 with our prime numbers that we ended at the end of our branches. So we got 2 times 3 times 3 times 3. And what we're looking for here is we're looking for a pair of the same numbers, right? And I see here that I have a pair of 3's. So these pair of 3's, what we're going to do is for every pair of the same number, we're going to cross it out and we're going to pull 1 out. Right? And the reason for this is because it's understood that this guy right here, 3 times 3, it's really just 9. So it's like we're taking the square root of 9, right? And this is the reason why just 1 3 comes out. So we have 1 3 that came out, and underneath the square root, what we're left with is just, well, 2 times 3, which we can understand is just 3 times the square root of 6. Right? And so that's how we simplify these radicals using prime factorization or that factor tree method, right? We'll go through this next one here a little bit faster. Now we're looking at 2 times the square root of 50. What we understand here is that the 50 can be broken up into 2 times 25, 2's prime, then this gets broken down into 5 times 5. So as I replace this, one thing you want to make sure that you're being careful of is you'll notice that this one already has a 2 on the outside. Don't forget about that 2. So I'm going to write that 2. And then we have the square root of, instead of 50, we're writing down the product of our prime numbers. 2 times 5 times 5. And so what I see here is we have a pair of the same number. We have a pair of 5's, right? And so what we're looking at here is, well, 5 times 5 is 25. So it's like the square root of 25 here that I have circled here. We understand that that just gives us a 5 now on the outside. And what you'll notice here is that we have a 5 and a 2 on the outside with under the square root, all we have left remaining is 2. So what you might be wondering right now is, what am I supposed to do with the 5 and the 2 outside the square root? If you have multiple items coming outside of the square root, it's understood that we're going to multiply those values together. So this becomes 5 times 2, which would be 10. And 10 square root of 2 would be our simplified form for 2 root 50. And then we'll move on to the 108 one. So we'll look at this one. If I want to break this down, again, the advice is if you're getting to a number that's a little bit big and you don't have a calculator, if it's an even number, you can always break it up by 2. So 2 times 54 would work for us here. I know that 54 can be broken down into, if I want to keep going by 2s, 2 times 27, 2 is prime. 27, I know 3 times 9, and then 3 times 3. So we end up rewriting this, and what we have here is we still got that 4 out in front, so we got 4 square root of, and now we write down all of our prime numbers. 2 times 2 times 3 times 3 times 3. And we're looking for a pair of the same numbers. Well, I see here I got a pair of 2s, so 1, 2 comes out. I see here that I got a pair of 3s, so a 3 comes out, right? So sometimes you're going to have multiple pairs of the same numbers, right? So we had a pair of 3s, so 1, 3 came out. We had a pair of 2s in blue, so 1, 2 comes out. And then we had that original 4 that was on the outside. And all we have left underneath the square root now is, well, just the square root of 3. All we have to do now is just multiply the numbers out in front. 3 times 2 is 6. 6 times 4 is 24. So we get 24 times the square root of 3 as our simplified radical for number 3. And so this prime factorization, this factor tree works pretty much every single time. And I recommend that you're familiar with this method because sometimes you're going to get numbers that can get pretty big. And this kind of helps break down those numbers to become a little bit more manageable. The next way that I want to show you guys how to simplify radicals is going to be by using perfect squares. So this method is going to require you to know your multiplication facts, and it's going to require you to make sure that you know your perfect squares, right? For reference, our perfect squares are written over here to the right. Our perfect squares are listed down below. All right, we got 4, 9, 16, 25, 36, 49, 64, all the way to 225. I'd recommend trying to have these memorized at least 1 through 15. So the way that we're going to do this is in these 3 steps. What we're going to do is we're going to break up the 72, but we're going to break it up so that one of those numbers is a perfect square. Specifically, I want to look for the largest perfect square factor for that number. From then, we're going to rewrite the radical as the product of both factors, and then we're going to simplify the perfect square. So what we're doing here essentially is for the square root of 72, we can break this up as, well, I know 36 times 2 gives me 72, and I'm breaking these down as separate square roots, right? 36 times the square root of 2, that would give me a square root of 72. But it's understood that, well, the square root of 36 is just 6, so we get 6 square root of 2. And this way, you're going to realize it becomes a lot more efficient for simplifying radicals. But again, you need to know your multiplication facts and your perfect squares. So if I look at the next one here should be hopefully a little bit more obvious. I can break up the 300 into a product of perfect squares. I understand that, well, 100 times 3 gives me 300. And I know that the square root of 100 is 10. So this simplifies to 10 root 3. And so I like this method a lot better because it just lets you work a lot faster. So we'll go ahead and keep it moving here, and we just want to go over how is it that we add and subtract radicals. So when it comes to adding and subtracting radicals, the radical must be the same. So the only way that you can add and subtract radicals is that the radicals have to be the same. So for example, look at the green check mark here. You'll notice here that the square root of 5 and the square root of 5, the radical, the number underneath it is the same, right? So I got square root of 5, square root of 5. If that's the case, then we can simply just add the numbers that are out in front, right? So 3 plus 4 gives us 7, and the radical, the square root, just stays the same. What you'll realize here is that we end up with where we can't add. We have a situation here where maybe we have the square root of 5, and the other square root I'm trying to add to it is the square root of 2, right? These are obviously different. I cannot add those, right? So if I wanted to simplify an expression, I would need to just leave it as is. I can't simplify that any further. So let's just practice with some examples here down below. So it says, what is 2 square root of 32 plus 4 square root of 50? Well, let's break this one down. I know, and we're going to simplify the square root of 32 using the method that we just discussed. I can break this down into 2 times the square root of 16 times the square root of 2. I know 16 times 2 gives me 32. Now, we understand the square root of 16 is just 2 times 4, and we're left with square root of 2. 2 times 4 is 8, so 8 root 2 is what this simplifies to. If I simplify the 4 root 50, well, I have 4. Square root of 50 can be broken down into, well, I know 25 times 2 would still be 50. And I'm doing this strategically because I know that the square root of 25 would just give me 5. So this 4 times square root of 25 would basically just be 4 times 5. And then we have our root 2 at the end. 4 times 5 gives us 20, so we got 20 root 2. So what we're doing here is we're adding these guys together, right? And what you'll notice here now is, well, look at those square roots. Those square roots happen to be the same number. So that means that we can just add the values out in front, right? So the 8 and the 20. If I were to combine those, 8 root 2 plus 20 root 2 would give me 28 square root of 2, right? So when you're checking to see whether you can add or subtract radicals, please just make sure that you're simplifying before assuming that they cannot be added or subtracted. So looking at the next one, okay? Next one, we got 75, root 75 minus root 27, right? This root 75, let's break it down into 25 times 3. I know 25 times 3 gives me 75. Square root of 25 is 5. So 5 root 3 minus, well, if I break down the 2 root 27, I'm sorry, just the root 27, I can break this down into 9 times 3. Square root of 9 is simply just 3. So we got 3 root 3. And if I subtract these values, we see here that the square roots are the same again, so I can work with those numbers in front. 5 minus 3 would just give me 2. So this is 2 square root of 3, right? And so just to summarize, when you're adding and subtracting radicals, you can only do this when the radicals are the same, right? So that same number under the square root would be the criteria for us to be able to add, right? I realized that we left a blank here on the second bullet point. It says simplify radicals if necessary, add or subtract the numbers in front, but leave the radicals the same, right? And so next we'll look at multiplying radicals, right? When it comes to multiplying radicals, the way that we do this is you multiply the numbers in front, and then you multiply the radicals, okay? And you'll simplify the radicals at the end if necessary, right? So you can simplify them at the end or you can simplify them in the beginning. Truly, it's up to you, right? So if I look at this example here, what we're saying is if I'm going to multiply radicals, you multiply the numbers in front of the square root together. So 4 times 2 gives me 8. And then you multiply the numbers underneath the radicals together. So 5 times 15, if we multiply that, we get the square root of, I believe it's 75. So 8 square root of 75. And here we want to make sure that we leave our answers in simplest form. The 75 can be broken up into 25 times 3. And so we're left with 8 times the square root of 25 is 5. And then square root of 3. Now just multiply. 8 times 5 is 40. So our answer is 40 square root of 3. Right? So always get in the habit of simplifying. At the very end, we want all of our answers in simplest form. Right? Same idea here for the next one. If I want to multiply 3 square root of 6 times 5 square root of 20, well, you multiply the numbers out in front. 3 times 5 is 15. And then you multiply the numbers under the square root together. So we got square root of 6 times square root of 21. 6 times 21 gives you 126. So we got 15 times square root of 126. And if we look at this next one here, what I notice here is root 126. I can't think personally off the top of my head of the largest perfect square that fits in that. So these are situations where the factor tree comes in handy. I know I can break this down into 2 and 63. And as you start to do the factor tree, you'll start to kind of realize what that perfect square is, right? So I'm starting to realize here that the perfect square that fits inside of that is actually 9, right? 2 is prime, though. I'm just going to keep going with this method. 9 can be broken down into 3 times 3. And then 7 is prime. So as we rewrite this, this becomes 15 times the square root of 2 times 3 times 3 times 7. I see that I have a pair of 3's here, right? So this is really just the square root of 9, which is 3. That's the reason why we just pull a 3 out. And what we're left with here is 3 times 15 out in front, which is going to give us 45. And underneath the square root, we have 2 times 7, which is 14. So our final answer here in simplest form would be 45 square root of 14. Right? So just to summarize, multiplying radicals, you multiply the numbers in front together, and then you multiply the numbers under the square root together, right? And simplify your answer at the very end. So now we want to get into probably one of the most important concepts that we're going to be using throughout chapter 8, which is going to be covering how do I rationalize denominators, right? So before we begin, when we're rationalizing, it's understood that when we're simplifying radicals, you cannot have a radical in the denominator, right? You just can't. If you do, then that is not in simplest form. So for us to better understand the process of rationalizing, let's consider the following. Okay, look at these numbers here down below. 7 divided by 7, that's just 1. 12 divided by 12, 1. 3,542,127 divided by 3,542,127 is just 1. And if I look here at the very end, the square root of 5 divided by the square root of 5, well, that's just also 1. So what conclusion can we make from these examples here? Hopefully what you're thinking right now is that any number divided by itself is always going to be 1. So as we looked at the examples, you pretty much have the same thing on top and bottom. So any number divided by itself is always going to be 1. A really important concept to know for really any subject in math. Now I want you to consider the following, okay? Now consider for the problems down below. 4 times 1, well, that's 4. 735 times 1, well, that's 735. 9,133 times 7 over 7, well, let's take a look at that 7 over 7 again. 7 over 7 is pretty much just the same as multiplying by 1. So 9,133 times 1 is just 9,133. So as we look at these examples, what conclusion is it that we can make? What we can understand here is that any number times 1 equals itself. So in other words, if I were to take a number and multiply it by 1, I really wouldn't be changing it numerically, right? For example here, 4 times 1, well, me multiplying the 4 times 1 didn't change anything. It's still 4, right? What we're going to do is we're going to combine both of these ideas here, right? The idea here in what I have starred here in blue, the fact that any number divided by itself is 1 and any number times 1 equals itself. We're going to put these together to help us rationalize denominators here with square roots. So the way that we're going to do this is we're going to simplify these examples down below by multiplying the top and bottom by the radical that's found in the denominator. So for example here, let me zoom in so it's easier to see. In the example where we have 2 divided by 3 square root of 5, what we're saying here is if you want to simplify this square root, multiply the top and bottom by the square root found in the denominator. The square root in the denominator is square root of 5. So what we're going to do is we're going to multiply the top and bottom by square root of 5 over square root of 5, right? Recall from earlier that, well, we said earlier that the square root of 5 divided by the square root of 5 is just 1. So all we're really doing here is multiplying this by 1, which isn't really changing this numerically. But this works to our advantage because now, as I look at the top, on the top I have 2 times the square root of 5. When you're multiplying fractions, you multiply straight across the top, straight across the bottom. So we have 2 square root of 5 on the top, but on the bottom, based off of what we learned earlier, when you're multiplying square roots or radicals, you multiply the number outside and those together, and then you multiply the numbers inside the square root together. So while the square root of 5 doesn't technically have a number out in front, we understand that there's technically a 1 there, right? So if I were to multiply the numbers out in front, 3 times 1 is just 3. And then if I multiply the numbers under the square roots together, okay, square root of 5 times square root of 5 would be, well, 5 times 5 gives me 25. So this becomes 3 times the square root of 25, right? Which could be simplified. That bottom part, we understand that the square root of 25 is 5. So this becomes 3, the square root is gone. The square root of 25 here is just 5. So this becomes 3 times 5 on the bottom. On the top, you still have the 2 times square root of 5. And if we simplify this, we have on the top still 2 square root of 5, but on the bottom, 3 multiplied by 5 gives me 15. So this process has gotten rid of the square root that's in the denominator, and now this is fully simplified, right? So to recap, anytime you want to rationalize a denominator, rationalizing is what we do when we're trying to get rid of that square root in the bottom. To rationalize a denominator, you multiply the top and bottom by that square root that you found in the denominator. So let's practice with another one here, okay? So if I see here 6 times the square root of 15 divided by the square root of 3, I can't have square roots in the denominator. To simplify, we're going to multiply the top and bottom by that square root found in the bottom. So multiplying top and bottom by root 3. If I look at the top here, we get 6 times, well, 15 times 3 gives me square root of 45. On the bottom, square root of 3 times square root of 3 is square root of 9, right? So we have 6 root 45 over the square root of 9 is 3, right? And now we can see here that looking at the 6 over 3, I can actually simplify that. 6 over 3 simplifies to just 6 divided by 3 is 2. So we have 2 times the square root of 45, which the square root of 45 can even be simplified, which if we look at this, we can break up the 45. I'm going to leave the 2 out in front, but the 45 can be broken up as 9 times 5. So square root of 9 times square root of 5, we know square root of 9 is 3. So this becomes 2 times 3 root 5, which gives us, well, 2 times 3 is 6. So 6 square root of 5 would be our simplified form for this last example, right? Alternatively, we didn't have this in the notes for today, but it's understood that, well, if I'm multiplying, when multiplying, we multiply the numbers in front and we multiply the numbers under the square root, then the same could be implied for division. We could have done this a lot faster by just looking at this part here highlighted in orange, right? If I wanted to divide 6 root 15 divided by root 3, you pretty much just could have divided the square roots, right? So if I write that over here, dividing the square roots would literally just be 15 divided by 3, which is 6 square root of 5, which gets you the same answer that we did earlier. Again, a little bit more faster, but the idea behind me showing you that first was to get you to understand how to rationalize a denominator, all right? So to summarize, when you're rationalizing a denominator, getting rid of a square root on the bottom, you multiply the top and bottom by the square root that was found in the denominator. All right, but that'll be the end of the notes for today. There is no homework assignment for today, just a quick recap on how we simplify radicals.